Qiang completed his PhD here in 1989. I was his PhD advisor. He was a professor in Canada for about 10 years, and then he moved to the Hong Kong University of Science and Technology. He currently has an endowed chair, and in addition, he's the head of their computer science and engineering department. He has a hugely influential set of academic publications. His HDEC index currently is 89. In addition, he has founded two major journals, the ACM Transactions on Intelligent Systems and the IEEE Transactions on Big Data. He is a fellow of four major professional organizations, the AAAI, the IEEE, the IAPR, and most impressively, the AAAS. Finally, he's a member of our department's Alumni Hall of Fame. Qiang, I'm very proud of you.
Thank you. Thank you, Dina. So let me get started. Thank you everybody for coming on this Monday afternoon, right after Thanksgiving. So my talk title is right here, when transfer learning is deep learning. You must be curious about this title, especially everyone has heard about deep learning, but not so much about transfer learning. So let me tell you from the beginning. Now, everyone has heard of AlphaGo, right? This is the reason why AI had such a recent surge of interest in AI. But do you know what AlphaGo cannot yet do? Okay, so this is my point. So if you take a certain sized board and had an AlphaGo trained perfectly for this board, but if you change the size of the board, then AlphaGo has to be completely retrained for that board. Okay. Now, if you take that even further, if you train AlphaGo for the game of Go, and if you take it to a different game, say chess, then AlphaGo cannot adapt itself, at least not yet, at least not without transfer learning. Okay. So what is transfer learning? Transfer learning is our ability to adapt from one skill to another. So for example, as humans, we learn how to ride bicycles. And so we find it very easy to adapt to riding a scooter, motorcycle. Okay. By the way, this is transfer learning in Chinese. I bet you can figure that out. Okay, transfer learning is not yet as hard as deep learning, but it will not take long. Okay, so recently some leaders like Andrew Yang has openly spoken about transfer learning as being maybe the next big thing after deep learning. Okay, so this curve is due to him. Where along the timeline, the next curve to rise is marked transfer learning, and there's a reason behind it. So I'm going to explain that reason. If you really want to find out about transfer learning, you can check on Google Scholar. And so this is a recent check on Google Scholar, ranked by the number of citations. The first in the list is a paper written by my student and I, known as a survey on transfer learning. Currently it has more than 3,000 citations. The second one was written by Andrew Yang and students on self-taught learning. And the third one was again written by a student of mine and myself, known as Boosting for Transfer Learning. And this one has over 1,000 citations today and rising quickly. Okay, so reason why I'm showing this is because I want to share the excitement with you that this transfer learning is catching a lot of attention, particularly due to some apparent limitations of deep learning. So what are some of the limitations of deep learning? First of all, when we look around, especially in our everyday life, not very often do we have big data. We often have small data, small amount of data. Okay, data that are sparsely labeled annotation, data with a lot of noise, a lot of wrongly labeled data. So when we take a big data and train a model, but we wish to extend or generalize or adapt that model to a neighboring domain, to a related domain where there is only small data, and we wish that model to still work. Okay, so this is a practical concern. In industry, when you look at, so for example, medical imaging, okay, domain. So we did a recent survey in order to find a student of mine a feasible research topic for his PhD. And we collected all sorts of public data. We found only, domains with maybe 400 or 500, at most 600 labeled images, and anything beyond that is beyond public reach. Of course, there are hospitals with tens of thousands, but they are not releasing them. In education is another area where the interaction. So a recent book instructor said he had 20,000 students in his class. He was very excited. But when we looked at the interaction data between him and his students, the data is extremely sparse, cannot be used to train an automated chatbot. Okay, so these are examples where the frustration came from. Another reason for motivation for transfer learning is because, unlike software engineering practice, many machine learning researchers do not pay attention to reliability and robustness. Okay, when you have a mission-critical software, such as a statistical model, and when you tweak the underlying data a little bit, when you tweak the model a little bit, it often fails. There is a dramatic drop in performance, and this is not acceptable, okay, in the real world. So we wish to extend the model to other situations, to neighboring situations, by changing the environment by delta. We don't want the environment, the model to change by an exponent of delta. And finally, we are in the era of personalization, right? Everybody carries a mobile phone. We look at news on the mobile phone. We talk to people. So we wish the phone to know us. Now, how do you do that? How do you ensure that a recommender system operating on your phone to know about you? Well, our current way is to upload all our data to the cloud, right? And then let the machine train a system with our preferences, with our bias, and then download the resulting model to our phone. So this process actually leaks our data to the cloud. Okay, so when you are very concerned about privacy, this could be a problem. Now, an alternative is to train a universal model in the cloud and download that model to your phone and have it adapted right on your phone. Okay, imagine our phone will become ever more powerful in the future. So the training, the adaptation can be done on your phone. And in the whole process, there's no bidirectional movement of the personal data. Okay, thus protecting the environment. So we are working on a model of this to really solve this privacy issue on its root. But when you work on transfer learning, you know it's very hard. So I took this slide actually from the web. Somebody else already made this slide, not from learning, not from machine learning. This slide came from education psychology. Okay, in the field of education, this term called the learning transfer has been around for over 100 years. Okay, where people have, there's a branch of this education theory that believes that the metric to measure whether a teacher is good is whether the student of that teacher can easily adapt, okay, knowledge from one area to another, from one class to another, from planning to machine learning. So data must be a good teacher. Learning transfer is such a measure. But okay, it's the same idea, transfer learning. But it's hard. And the primary reason for why it's so hard is because when we compare two domains, and when we want to transfer knowledge from domain A to domain B, what we are doing is we are looking for invariant. Okay, we are looking for domain invariants. For those in programming language, looking for invariant in a programming property is a way to prove correctness. And here, looking for invariant is a way to transfer knowledge. So let me use this example which I personally experienced. Okay, if you drive in the US, it's like this, right? The driver is on the left-hand side of the car. If you drive in mainland China, it's the same. Whereas if you drive in UK, or if you drive in Hong Kong, the driver is on the other side. And I don't know how many of you have the experience of renting a car and start driving and run into trouble, okay, on the wrong side. I have, okay, it was very dangerous. But knowing transfer learning can save your life. And the key is this: you look for invariant. Now, who can tell me what the invariant is from these two pictures? Okay.
Well, the invariant that I was told was you always keep the passenger side near the curb.
That's right. That's why you're still online. I say that because Dave goes to Hong Kong all the time. Yes. Now, so the invariant, the other way of saying it is the driver is closest to the center of the road, okay, or the passenger side is always closest to the curb. If you do that, you switch immediately. And if a system can find that, this is the key to transfer learning. Okay, this is the invariant. So our job is to enable a system to do that. And so how is that done? And this picture on the right illustrates that. Let's say the green part is one machine learning domain and the red is another. This domain is known as the source domain. This is where you have a lot of data. This is new, the red is new. And now you wonder how you can transfer much knowledge to the red part. And the key is to find the knowledge that's invariant, that's common to both the red and the green, and then transfer it this way, okay, and move the knowledge that way. So there are various ways to do this. And here is a simple summary. Sorry for the small word. So the green part says instance-based approach. This is one class of algorithms that can look for this invariant. Another one is known as feature-based approach. A third one is known as model-based. And the last one is relational-based approach. So these four approaches pretty much cover all methodologies in which transfer can occur. For example, for instance-based approach, let's say you have lots of photos from, say, ImageNet in the source domain with labels. And if you're only interested in a particular kind of pictures, the instance-based approach is to look for similar images to the target image and give them higher weight. And as a result, you boost the training data by making multiple copies of similar source domain images. Okay, so this is the idea behind the so-called instance-based transfer. Whereas the feature-based transfer is to compare the two domains and map both into a subspace. In that subspace, the two look exactly the same, identical. Okay, you remove all the different features and the result is the same. You can even extend this to an area where these two domains look like completely different, but they have similar meaning. So this is a Chinese poem, this is a Chinese painting, they express the same thing. Okay, so far I've been talking academic, and these are just maybe live on the research papers, but I should tell you that transfer learning is already taking place in industry and making a huge impact. And so here's one example before we go into further details. So this is a company created by my student, and it's in Beijing. It's called 4 Paradigm. What it does is it does all sorts of machine learning projects with banks and financial institutions, and they have this particular problem of modeling credits, okay, loan credits for buyers of luxury cars. Now, as we know, luxury cars are sold to people with lots of money, right? And those people are very few. And so as a result, the samples are very scarce, very rare. And so with just these samples, you cannot build a credible model of luxury car purchases. So what they do is they go to small loans, the so-called micro loans, where the loan is in the order of maybe 1,000 to 5,000 US dollars maximum. And those loans can be in the order of 100 million a year. Okay, so with that data, you can build a model, but that model is for macro loans. So there's a difference between micro loans and large loans. Now, transfer learning allows you to remove that difference and look for what's common. And so by using this transfer learning, they were able to increase the effect by 200%. So it was very effective and is being used by the bank. Now, this is the first part of the talk, which is introducing what is transfer learning. Remember, the title of the talk is When Transfer Learning Meets Deep Learning. So now we have to enter the world of deep learning. Now, so first let me give you the analogy of transfer learning used to be done like this, like building a one-story house in the Chinese architecture. But when you go deep learning, you have multiple levels that brings extra elegance, extra. So in other words, what you can achieve here, you can achieve more by being more quantitative. So here is the qualitative work. So let me give you an illustration of that. So this is a deep learning model turning sideways. Okay, so the input is here, the output is here. So this multiple layer is here, right? So roughly, deep learning is doing nonlinear transformation between layers and using, CNN or using ResNet or whatever transformation. But the architecture looks like this. So let's say the blue is one domain where we have built a very credible and reliable model. Now suppose we have a new domain where we don't have so much data, but we built a rough model. So we are interested in how much knowledge in the blue domain can be transferred to the red domain. Now, deep learning allows us to answer this question layer by layer. So we can ask how much is the first layer transferable? How much is the second layer transferable? Under what condition? Okay, so in other words, we can, for example, draw a relation between these corresponding layers, and we can ask what the differences are between these top layers. So these are known as domain distance. We can now finally ask about this distance layer by layer. So there's this recent paper by Banjo et al. Asking exactly this question. So my student looked at this and thought, what an interesting idea. And so what about other work that mixes transfer learning and deep learning together? First of all, do they give us an extra advantage in terms of performance? And so this is the result of her investigation. So along the horizontal axis, we have the year in which this work appeared. And along the vertical axis, we have the performance. So this, you can consider this as 70% accurate. And without looking in details in the domain, we realize that those red ones correspond to transfer learning plus deep learning, and they generally give you higher performance than those that use a single layer deep learning, transfer learning. Okay, so if you use transfer learning alone, so this, for example, TCA was the result of another student of mine in 2011, also highly cited, near 1,000 citations, but gradually the citation rate is slowing down. Why? Partly because it didn't use deep learning, and this work that appears, so for example, this work is a result of a Tsinghua researcher working in Berkeley, and the result is like this. Okay, the graph is very ugly and sophisticated, but you can try to understand it layer by layer. So first of all, the first several layers is marked frozen. Frozen means from the source to the target, you transfer the whole thing as whole. You don't make any changes. The next several layers are marked fine-tune. Fine-tune means you allow the transfer to happen first as a whole, and then adjust it by minor twists. Okay, and the last several layers are marked with this thing called MKMMD, which is a distance measure based on multiple distributions, probability distributions, and the formula is written here. You're using kernels to measure the distribution and judge how much difference should we allow these two domains to have, and these correspond to their final tasks. So they are treated differently according to different layers. And so this is exactly the idea when we go a step further in terms of studying how transferable these domains are. These are 3 domains. This one is from Amazon. You can see Amazon has taken out all the background in order not to let people copy from their images. And these are from webcam and other domains. Then people have studied, so this work titled How Transferable Are Features in Deep Neural Networks, which appeared in 2014, quantitatively studied layer by layer. So this one is the first layer, second layer, this is the last layer. And there are several conclusions you can draw. The first one is that as you go deeper and deeper, the transferability actually goes down. Okay, so that means on these vision-based domains, lower levels represent more general and more transferable and more invariant features. The second conclusion is that if you allow things to change a little bit, so instead of frozen, you allow some fine-tune to happen, then this performance can come back. Okay, so and last one is when you really pull these 2 domains that are far from each other, then the performance can quickly go down. So this idea of deep learning and transfer together have to really watch out for the original distance between the domains. So based on this quantitative knowledge, we can then design a few engineering solutions. The first engineering solution is, what if we have unsupervised data? Okay, so we have unsupervised data in the source domain, we have unsupervised data in the target domain. Can we do any transfer? And so the idea is you can partition the layers into 2 parts. The first part is known as frozen or tied, and the second one is called adaptation. And here you can write the loss in terms of 2 losses. One is the loss on the source, and another one is on the target. And the loss can be described using any number of these losses. One is called discrepancy loss, adversarial loss, or reconstruction loss. I'm not going into any details of this, but these are engineering tools you can use. Now, once you have an additional labeled data, say in the source domain, then you can introduce another loss which represent the loss in the source domain, this Y source. Okay, and so this additional domain can give you an extra guidance. So the final picture then looks like this: a domain, a source domain that can reconstruct itself, a target domain that can reconstruct itself, and some paired loss if you have a mixture of the source and the target. Say you have a picture with some words in it. These are picture, these are words, and these parallels represent how much overlap you can reconstruct. So this corresponds to the traditional so-called multimodal. In other words, you have images and words mixed together, and you can handle all of this. Okay, so far we've talked about how to measure the differences between two domains, how when we have deep learning architecture, how to transfer from source to target while getting different losses to be represented in optimization to make use of this quantitative knowledge. Now let me go into some more interesting topics once we combine these two together. Okay, the first one is in traditional transfer learning, people have only considered two domains, right? A source domain and a target domain, and wonder how to transfer from the source to the target. Now, if we are a little bit smarter, we can think of not just one domain. Okay, so what if these two domains are far from each other? If they are far, then people in transfer learning said you cannot transfer. Okay, but what if you have some stepping stones? You have some intermediate domains like this. Okay, so you have a source domain that's far from the target domain, but you can find a few intermediate domains that take you from the original to the target. And this is exactly what this student did in a series of publications. So let me show you the architecture for that. Okay, so the idea is you have a source domain, you have a target domain. Say the source domain may be a bunch of text documents. The target domain is a bunch of images. So there's no way for the text to affect the image. But you have a number of intermediate domains. Some mixture of text and images appear in these intermediate domains that can pull together in a chain of connection. So like building a bridge. So for this, we can build a deep learning architecture, and we can feed it source data, intermediate data, and some target data with label. And in the process, we want to make sure that in this training will reconstruct source, intermediate, and target. At the same time, we'll pull together source and target by means of the intermediate. So whatever the intermediate can do to pull us together will show up in a classifier to have the correct performance. And when that happens, we add a weight an extra weight to the source data. And so eventually, when this system is trained, we will have a well-performed classifier based on the common intermediate data. Okay, so by means of just feeding this together, we can have this stepping stone effect. Now, how well does this do? There are various tests that my student has gone through, but recently we found this other work, which is highly related to be very interesting. And the work actually came from a joint work between Stanford and United Nations. And what they try to do is they take satellite images of the African continent, and from this image they try to infer the poverty level. Okay, so knowing the poverty level of a region allows them to decide on the support policy in order to give different area, different type of aid. Okay, so before this was done by sending investigators to the ground and investigating each region in turn, and it can be both costly and lengthy and very dangerous. So now the question is, can we just take a satellite picture and immediately come up with an answer? Okay, well, you can't, right? Because these are unlabeled. But you can be smarter, right? You can take the same region, you can take a picture at night. And the night picture are illuminated with lights, and usually we understand the lights represent the amount of light represent the amount of economic development, right? So this gives you a first-hand rough idea. But then how do you segment these? This can come from image depth, right? If we learn a good image segmentation software, then we can use that. We can use that model to segment the images, the light images, and then we can in turn use the light images to help label the date images. And if you keep doing this and train with a little bit of label data, then eventually we get pretty good result. And the result shows that using the transfer learning, they get 71.6% accuracy as opposed to 75.4 using the human labor, which is already getting close. So we are quite happy that somebody else did this work, shows the transitive method works. The second application, which is very interesting, is in sentiment classification domain. Okay, so the title is rather long, and let me speak the title and just directly tell you what it tries to do. Suppose on e-commerce, we try to allow users to comment on different products. Okay, so these comments can be like one of the best novels written by this author, excellent, I was disappointed. So things like that, right? So we have for different vertical domains, say on Amazon or Chinese Taobao, we can have a huge collection of these comments. And each one is about a particular product in that particular domain. So the question is, suppose we have built a credible model for, say, electronic products, how much of that is applicable to an entirely different product? So if we take that model as is and apply to comments of, say, videos, then dramatically we can see a downturn in terms of performance, right? That's reasonable because they use different terminology to describe the sentiment. So this is illustrated more clearly here. So this column here corresponds to the electronics domain, whereas this one, the video game domain. Here we have labels, we have thumbs up and down. Here we don't have any labels, and our task is to predict the labels on this side. But if we just read these carefully, we can find that they are all using different terminologies. Like this one says unit, this one says picture quality, whereas here it says hooked, this is plot. Okay, so they don't correspond to each other. But if we look even more carefully, we can find some words that are domain invariant. Remember at the beginning of the talk, I was talking about looking for invariant as the key of transfer learning. So these red marked words, pink words, are invariant between the domains. Okay, like good, and good here means positive sentiment. Excited and excitement means positive sentiment. So these words that are indifferent to the domains and yet reveal sentiment are known as pivot words. Okay, so because they connect different domains. So, okay, this gives us a hint. If we can find enough pivot words, then we can easily transfer the sentiment model from one domain to the next. So finding the pivot is the key. But how are people making use of the pivot? About 10 years ago, there has been two pieces of important work. One was by this guy called Qiang Yang. Actually, he was a researcher at Microsoft Research, and he actually spoke fluent Chinese. He worked in Beijing, Microsoft Research for a while, so we talk a lot. And his method was considered state-of-the-art at that time. But there was one drawback, which is he relied on people to pick out the keyword words. So it's totally manual. And because of this, it's very hard to scale. Okay. Then a student of mine, Pan et al., they started using an automatic method to find out pivot, but it's very rough to use clustering, spectral clustering in particular. Now recently, a group of deep learning researchers started looking at this and building the so-called black box model. They can make very accurate predictions of sentiment in one domain, but to transfer is still very hard. Okay, to transfer between domains is still very hard. Now when they can do the transfer, they cannot pick out the pivot words. Thus, the models are not very explainable. Okay, so earlier I was talking to students and I was saying that one of today's trends in deep learning is to come up with explainable models, explainable deep learning models. So then what do we do? Well, we have two goals in mind. One is in each domain, we want to find the pivots so that the models are very accurate. So in each domain, the sentiment has very high accuracy. Okay, so that's our number one goal. Number two goal is we want to find the words that are invariant, indifferent to the domains. So those words which we use to build the model have to be accurate in its own domain and have to be inaccurate when it comes to distinguish between the two domains. Okay, so these words have to be blind to the domain difference and have to be very sharp as to telling the positive from the negative. Okay, so two things. Now when we have these two things, it's almost like playing a game, playing a chess game, right? Somebody wants to maximize the score while another person tries to minimize the score. So the question is, can we use this mechanism to build a game? And the answer is yes. And yet we have a third constraint, which is we want the system to be a white box. We want it to tell us which words they are, the pivot words are. So in machine learning, there's a new technique known as memory networks, and it's able to pick out a so-called attention. So to put a long story short, attention is a way to give weights to important keywords when you perform machine reading. When a computer reads through a long text and can leave some memory behind, and the memory can answer certain questions. Okay. Now, you use multi-layer in order to keep track of those attention words which are ignored by the first layer. So here, a three-layer architecture is used. So this is one. Another one is, remember, we want the words that are picked to be pivot words. Pivot words, by definition, are indifferent to the domains. And so they must be very bad at classifying the source and the target. So we want the classification performance to be as low as possible, okay, between timing the source and the target. And then we want these two domains to work together, side by side. Okay, so this is an adversarial problem, and we want them to work side by side to share these attention words in the two domains. So eventually, this is the mechanism to make this work. So how does it work? Well, we took multiple Amazon domains and let them mutually transfer to each other in order to build the experiment. So the first one is comparing with the hand-picked pivots, and this one is the automatic one, the one with the deep learning method, adversarial deep learning method, and you can see it's dramatically higher in performance. Okay, and number two is comparing with the black box method, such as this one DANN, which appeared in last year, cannot pick out the important words. The performance is roughly the same, but the extra performance actually comes from the ability of our system to pick out these important words. Just to read them loudly, these words are great, fantastic, excellent, terrible, can't, uncomfortable, and so on. So they make a lot of sense, right? And these are yet another collection of these positive sentiment and negative sentiment words. Okay, so this is the second work of how to combine deep learning with transfer learning. All right, now let me end the talk by mentioning two also very interesting work on combining these two techniques. We also have a group of students working with chatbot. Okay, we know chatbot. We know, for example, Siri is a chatbot, right? Echo is another chatbot. IBM Watson is yet another. But there's actually two kinds of chatbot. One is the kind of chatbot that can just carry on the conversation without much of a purpose. Purpose is to have as long a conversation as possible. Another chatbot is like a student and a teacher, right? You wish the conversation to be as short as possible, right? You want some task to be accomplished. Let's say if you're talking on the phone and buy a plane ticket, you want that ticket to be bought instead of having this day-long conversation with the service person. And so this is known as task-oriented dialogue system. And here we are interested in building a personalized task-oriented dialogue system. Okay, so the system lives on your mobile phone and will based on both the general chat knowledge, general knowledge about the domain, as well as your own chat history, and can cater to your own preferences. So that's our goal. Now, wouldn't that be wonderful? Now, but this is a challenging problem because if we build this by transfer learning, we build a general model. How do we transfer to a individual's data when that individual's data is very, very limited? Well, so here I want to speed up a little bit and just directly tell you some of the assumptions we made. Okay, the first assumption is dialogue systems can be built using reinforcement learning. So for those who don't know what reinforcement learning is, it is a form of planning, okay, of moving ahead to meet a goal. Except it makes use of two concepts. One is a state, another is an action. Okay, so if you're in this state, you take an action, it takes you to another state, and hopefully that state is closer to the goal. Okay, so this is it. So in reinforcement learning, people try to use a function known as Q function to represent this overall progress or overall state in which there are two parameters. One is a state, another is an action. So in conversation, you can consider the conversation so far as the state, how much you have achieved, and what you will say next as the action. This is known as the speech act. So to personalize a general model, we split the model, the conversation model, into two parts. The green part corresponds to the general model, QG, and the personalized part corresponds to the QP, which is the personalized model. So everybody has the same QG, but different QP. So the question is, how do we learn this part? Okay, we ignore this part because there are various other methods to do that. So let me just move quickly and tell you that, in fact, we invented a gating mechanism. This is a switch. It can be 0 or 1. When you carry on a conversation, there is a probability at any moment you are talking about something in general. Okay, you are asking a general question about about purchasing a plane ticket, or if it's switched on, it's about a personal situation, personal preference. Do you still prefer the morning flight? Yes. Okay, so this one can learn to be switched on and off depending on the state of the conversation. And so, okay, so eventually we were able to to do a lot of experiment and show the performance is really high. Now, so just before I came on this trip, I heard that this paper was accepted by AAAI this year. So people who go to AAAI in New Orleans will get to know this paper and the content in more detail. Okay, so here's a baseline conversation between the user and the agent. Here is the personalized, so you can see that the length is a little shorter, right? So generally, this is the case. So this one, I just quickly went through to show you that using transfer learning and deep learning together is beneficial to building a personalized chatbot. I actually have a demo, but it's in Chinese. So I'll save that for later, okay? And finally, I want to show you something about how to use transfer learning for crowdsourcing. As we know, crowdsourcing is to mobilize a large crowd who are non-experts to perform a task, and statistically using the aggregate information in order to generate the final results, such as labeling a picture, right? So for example, if you have lots of pictures, you ask what species is in this picture, and the answer is dog. And of course, there are many people who don't give correct answer. Maybe because they don't consider it as a dog, or maybe because they are just out there to make random money. Okay, so they are not careful with their task. Now, so here we can use transfer learning to help with this. So let's say we have a domain which is represented by this row. We have another domain which is represented by this row. Now let's say we build some really good data somehow by this row. We have a lot of very reliable results on whether something should be approved or something does not belong to a class. Let's say we have done something really well there. Now, in fact, if for a new domain like this bottom one, if we are not sure whether the reader, the user is giving the correct label, what we can do is we can leverage the relationship between these two domains and learn about reliability of each user based on the task. Okay, so this is how you can use transfer learning for cross-sourcing. Is you can use the thing you transfer is the invariant knowledge about users' ability. So you use existing tasks to rank the users, and then you use the ranks that you learned to come back and rank additional new results. So I won't go into too much details of this, except saying that you can build build a latent model, or you can use a deep learning model for this, and the result can be rather effective. So in the interest of time, I will stop here. Let me summarize by saying that machine learning is to learn from lots and lots of data, and deep learning especially. But transfer learning is trying to break this weakness. The requirement for big data may not be necessary in the future for reliable learning if you can adapt from other learning models. And in fact, transfer learning and deep learning can work together side by side by quantifying which layer is more transferable and making use of that by different level of granularity in terms of the data. And using this technique, we have demonstrated in at least 3 different application domains that transfer learning and deep learning can work together really well. So thank you. Thank you very much.
In order to pick up the pivot words, one of the things that you needed to do, or at least you need to do, is to ignore the effects of negations, like great versus not so great. And in principle, I can imagine that causing some problems. In practice, I don't know whether it matters to a significant extent or not. I was curious what you think.
Yeah, right. No, so actually, pivot can be a phrase. So not so great itself is a pivot. Yeah. So in fact, when you apply transfer and deep learning together, you can consider every phrase to have a certain degree of pivotness and non-pivotness. So domain specific and domain independent. In that view, then you don't care so much about these preceding words.
Okay.
Can you go over again how you measure how every specific layer is transferable or not based on the two domains that you have?
Sure. Yeah. So you probably meant quantification, right?
Yeah.
Yeah. Right. So, for example, in this, yeah.
Right. So the y-axis is accuracy.
Yeah, accuracy.
Okay.
This is accuracy. Yeah.
And what is the x-axis?
The x-axis is the layer, right? So here, each layer you can use that layer as a feature vector, and then you can connect that directly with a classification.
Oh, so you use these as features, for example, in SVM or something like that.
That's right.
Okay.
Exactly. Yeah. Yes. And this is the performance.
Right. But if you have very few samples, like very few entity data in the target domain,
this is assuming you have enough data and how much you can do. Yeah.
So in general, you mentioned that the source and domain should be close enough that transfer can work. So is there a way that we can measure that beforehand, before just going to try and see what happens?
Yeah, this is the question asked for many transfer learning. I think this is the holy grail of transfer learning. People have devised, so first we have tried things like KL divergence, and it doesn't seem to be accurate enough. And then, so this thing using the so-called MMD, which is measure the mean of a general distribution, turns out to be more accurate, but not quite enough. So theoretically, there's a line of research that's potentially to be explored, which is how do you come up with a universal measure of any two data sets, how far they are and how transferable they are. So this distance is yet to be discovered.
But yet there is nothing strong.
Practically what people do is today is still by intuition. Yeah, still not very principled.
Would higher order moments help? Like, you know, variance and skewness?
That's right, for sure. They will help. In fact, when you go deeper, you are using higher level nonlinear features similar to what you have described. They help.
I have another question. Could you comment on minimizing the loss function, which is the summation of the loss of the source and the loss of the discrepancy?
Yeah, sure.
What is the challenge there? Like, is it computationally costing, or is it?
Right. So your goal is to have accurate, have a good model, have a high performance model here, but you are trying to make use of this source domain as auxiliary domain. So the three things you can do, there are three things you can do to make that happen. One is in the source, because you have lots of data, you can measure the loss in the source. You can try to minimize that. But that has to be related to what you do here. So you try to if you have some label data, then you try to minimize the performance, the error. But if you don't, then you can try to minimize the reconstruction error. But if you have some data that have a little bit of features from both, then you can have an additional called pair loss. which you add as a third term. So whatever you add here, the goal is you want to this process to happen in such a way that what you do here can influence what you do here.
I see. But I guess the question is, infrequently, do you observe learning difficulties in terms of minimizing these kind of loss functions? Because I've never done experiments like this. I just wanted to know whether it is easy to train.
Right. So depending on convergence rate, right? Convergence rate sometimes no, especially when you have two domains you have to deal with. Yeah. So typically, what you do is you build this domain, and when you train on this, you try to move a portion of this over. So it's not done simultaneously.
I see. Do you think there is potential for more research in this area?
Yeah, definitely. Yeah, I think this kind of thing has this kind of architecture is very interesting, and people now use GAN, generative adversarial network, to try to simultaneously minimize the domain difference and maximize the performance of each domain. So this can be done that way. So architecture-wise and optimization-wise, they're done.
So it sounds like you described two architectures. Like one is like a Y, shared and then split. The other one was an X, where it starts separate. There's a common representation, and then it goes out.
That's right.
So the first one, I think of it as kind of understanding the shared perception, right? How to deal with input, and then specialize for a given task.
Right.
The second one is kind of learning what's common core concept that could be applicable for both tasks.
Exactly.
So for the end-to-end curve, which one of those is the one that gives us that? Is it the ability to transfer easily from the same input to different kind of tasks, or actually learning some really deep conceptual things that are knowledge, that's knowledge that you can transfer from?
I think what Andrew Ying's curve refers to more is only in image domain.
Right.
So it's the same input. It should be a Y.
So it's an issue of perception, shared perception.
For X, it's more ambitious, because you can have entirely different signals that share the same semantic core. People have tried that. For example, in multimodal, one coming from text, another coming from images. That can be done in some special cases, such as you have lots of web pages with both reels and images. Yes.
Could you talk about the relations between transfer learning and recent works like meta learning?
Meta learning. Oh, I have to learn more about meta learning. Maybe you can say a few words.
Meta learning is basically to have a meta learner trains several tasks, not only learns what the parameters should be, and then they can transfer to a new task.
Okay, so I guess there are some commonalities. So I would mention another. Maybe when you say meta learning, it's more related to lifelong learning. Lifelong learning is something which repeat transfer learning on an indefinite course. So the system can accumulate knowledge whenever it can, and it never goes down. I guess meta learning is trying to learn some commonality among tasks, and so when you deal with a new task, it's trying to use these meta parameters to save some extra work, right? So the spirit sounds like transfer learning, but maybe there are also differences. Yeah, I'd like to know more about that. Thanks. Yes.
Hey, Chen, this may be a little tangential, but does the transfer learning have any practical applications or TensorFlow optimization?
It does.
I mean, what Google's doing with TensorFlow for training their deep models.
It does.
Would this apply to that?
Yeah, because you really have two dimensions when you come to TensorFlow type of optimization. One is you will build better architecture, right, within this domain. Another one is across different domains. You try to reuse as much what you have learned as possible, right? So if you can recognize two domains where the difference is rather small, then you don't have to start from scratch. You can usually, so in the image domain, you just train the top two layers, and that's enough. In the best case. So this effort in optimizing TensorFlow, I think it can take on these two different directions. There's also a lot of work on building at the bottom layer, at the network layer. There are several efforts I know from the system side. Also try to make the system train faster. Yeah. So the answer is yes.